Welcome you all in my next lecture. So, in my last lecture I talked about, or I have introduced the notion of sequences in the n-dimensional Euclidean space. Now, today this lecture I will talk about the convergence and the notion of Cauchy sequences, and then I will talk about the definition of functions from n-dimensional Euclidean space to m-dimensional Euclidean space, and if time permits then I will talk about the notions of limit and continuity. Okay. So, what is the notion of convergence in sequences in Rn? So, let me just see what is the meaning of convergence of sequences in R. Okay. So, what is the definition of convergence? So, you start with a sequence xk in R. If there exists a number or there exists an element L in R such that for each epsilon positive, if I have a positive number capital A naught such that the distance between xk minus L, which is less than epsilon, for all k greater equal to N naught, then I will say that my sequence xk converges to L. So, what is going on? So, that means I am starting with a positive epsilon. I am saying that if I take any element from the tail of the sequences, the distance between the elements from the tail of the sequences and L, which is very small. So, if that things happen, then I will say that my sequence xk converges to L. Okay. So, the element L is called the limit of the sequence xk. I will write it xk converges to L, or this is sometimes I will write it limit k approaches to infinity xk is equal to L. If a sequence xk is not convergent, then I will say that it is not convergent, I will say that the sequence is divergent. Okay. So, now it is clear that what is the meaning of convergence in sequences, convergence of sequences in R. Now, later you will see I will introduce the similar sort of notation in the context of Rn. Let us see. Okay, before that let us see some examples of sequences in R. For example, if I consider the sequence 1 by k, then one can check that it is actually converges to 0. That means I can make the distance between elements from the tail of the sequences and 0 less than epsilon for all k greater equal to N naught, and that is possible by Archimedean principle. So, therefore, I can say that this sequence converges to 0. Now, if I consider this sequence xk is equal to c, that means all terms are fixed. This is called a constant sequence and it is always convergent and converges to the point c. Now, if I consider this sequence xk minus 1 to the power k, what are the elements of this sequence? This sequence like minus 1, 1, minus 1, 1, minus 1, 1, so on and so forth. This sequence is not a convergent sequence, it is actually oscillating. First term is minus 1, second term is 1, third term is minus 1, fourth term is 1, so on and so forth. So, this is not a convergent sequence, that means it is a divergent sequence. In other words, it is an oscillating sequence. If I take xk is equal to k, that means it is the sequence 1, 2, 3, 4. This sequence is also not a convergent sequence, it is a divergent sequence. That means I cannot find any real number L in R such that I cannot make the distance between that real number and the elements from the tail of the sequence very small. I cannot do that because it is actually increasing 1, 2, 3, 4. So, therefore, it is a divergent sequence. Now, I have the notion of convergence of sequence in Rn. So, start with a sequence capital Xk in Rn. This is the sequence I have already introduced the notion of sequences in Rn. Now, what is the meaning of convergence? If there exists an element capital L in Rn such that for each epsilon there exists a natural number N naught such that norm of xk minus L which is less than epsilon for all k greater equal to N naught. So, given epsilon, so the N naught that should depend on epsilon, you should write. Okay. So, therefore, given epsilon I have a point N naught such that if all k greater equal to N naught, if the norm is less than epsilon, then I will say that the sequence xk converges to L. Now, what is the difference between the convergence of sequence in R and convergent sequence in Rn? The concept is almost same. So, what I am doing is that just to replace mod in R by norm of the corresponding distance in Rn, rest of the things are same. So, therefore, I have a sequence capital Xk. I will say that capital Xk, the sequence in the n-dimensional Euclidean space converges to capital L if given epsilon, if there exists a positive number N naught such that norm of xk minus L which is less than epsilon for all k greater equal to N naught. That means I can make the distance between the limit L and the elements from the tail of the sequence is very small, then I will say that this sequence is convergent. So, I will say that element L is called the limit of the sequence. I will write capital Xk converges to R. I think this is the best notation. You write limit k approaches to infinity, capital Xk is equal to L, capital L. If the sequence is not convergent, then I will say that my sequence capital Xk is divergent. Okay. So, what is the moral? Moral is that convergence of sequence in Rn is essentially same as that of convergence of sequence in R. So, that means whatever the notion of convergent sequence in R is there, similar sort of notion is there in the context of n-dimensional Euclidean space, just I replace modulus by the corresponding norm or distance in the n-dimensional Euclidean space. Okay. Now, this is, as I told you earlier when I introduced the notion of sequences in Rn, that means it associates the corresponding n component sequence in R, and as I said there should be relations between the convergence of sequence in Rn and convergence of component sequence in R. So, this is the theorem. What it says is that you start with a sequence capital Xk in Rn, start with a point say capital L in Rn, this is point in Rn. Look, then it says that the sequence capital Xk converges to L if and only if all the component sequence Xkj in R converges to the corresponding Lj for each j is equal to 1 up to n. So, that means if I know the convergence of the sequence capital Xk to L in n-dimensional Euclidean space, then it implies the convergence of the component sequence in R. If I know the convergence of the component sequence in R, it will imply the convergence of the sequence capital Xk in Rn. That is what. So, let us see the proof. So, this is the forward direction. So, that means what I have in my hand, that means capital Xk converges to capital L in Rn, that is there. I have to show that each of the component sequence should converges to small Lj. How do I prove it? Okay. So, that is I need to prove. So, that means I have to make the distance between the elements of the sequence Xkj minus Lj very small whenever k is large. That is what I have to do. And this should true for all j running from 1 up to n. Okay. So, first thing you should observe that capital Xk converges to L, that is given. Now, if I compute the distance between Xk, capital Xk and capital L, which is nothing but norm of Xk minus L, and I know by the definition which is nothing but square root of Xk1 minus L1 square dot 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 Xkn minus Ln. I think that Ln should be suffix. Okay. Now, you see this is the sum. So, that means what I have? I have Xk1 minus L1 square up to Xkn minus Ln square. Now, it is sum of n positive numbers certainly which is less or equal to Xkj minus Lj square. So, sum of n positive square of n positive numbers which is always greater or equal to sum of the component, then what I am doing is that I am taking the square root and which is certainly greater or equal to modulus of this, and that is exactly I have written. So, therefore, I have the estimate. So, that means norm of Xk minus L which is greater or equal to modulus of Xkj minus Lj, and this is true for all j in between 1 up to n. Then what I will do? Given that capital Xk converges to L, so that means this side I can make less than epsilon whenever small k is greater or equal to capital N naught. So, that implies that this small Xkj minus Lj given epsilon, I can make it less than epsilon for all small k greater or equal to capital N naught, and it implies the convergence of this sequence, and that exactly I have written. Yes. So, look, so given Xk converges to L, suppose epsilon is positive given. So, therefore, there exists a n naught belongs to capital N, this is given, that means norm of Xk minus L which is less than epsilon for all k greater or equal to n naught. Because of the inequality I have proved in my last slide, so therefore, this is less or equal to this, therefore, which is less than epsilon for all k greater or equal to n naught, and this is nothing but the definition that this sequence converges to Lj as k approaches to infinity. So, therefore, if the sequence capital Xk converges to capital L in Rn, it will implies the convergence of the component sequence in R. Now, let us see the converse. So, that means I have the assumption that small Xkj converges to Lj as k approaches to infinity for all 1 less or equal to j less or equal to n. I have to show that capital Xk converges to capital L whose components are L1, L2, Ln. Okay. Let us see. So, start with a epsilon which is positive. Now, this is nothing but the adjustment. So, I am writing a epsilon star which is epsilon by square root of n. We will see later that with this some adjustment it is needed. So, given that epsilon star, since this is convergent given, so therefore I can have the existence of n star in n such that this is lesser or equal to epsilon star, and this should be true for each j and k greater or equal to n star. So there is a little argument is left behind, which is the following. See how many sequences I have. So I have a sequence x k1 which is converges to L1. I have a sequence x k2 which is converges to L2. I have a sequence x kn which is converges to Ln. Okay, this is given. So now given epsilon star, what will happen? I can make the distance between x k1 and L1 which is less than epsilon star for all k greater or equal to some n1 star. That I can do, right? Because this sequence x k1 converges to L1. Now what will happen? X k2 converges to L2. Same epsilon star if I apply, so I can make x k2 minus L2 which is less than epsilon star for all k greater or equal to some another n2 star. Okay, I will get. So if I go on like that, then for the sequence for same epsilon star, I can make, because x kn converges to Ln, so therefore I can make x kn minus Ln which is less than epsilon star for all k greater or equal to say nn star. Then what I will do? I will do that, okay, take capital N star which is nothing but maximum of your n1 star up to nn star. And this capital N star will work such that xkj minus lj which is less than epsilon star for all k greater or equal to n star, and that should true for each j. That's the adjustment you have to do. So that means each component sequence convergence will give you the existence of n1 star, n2 star, nn star. You take the maximum, and that maximum will work for all j running between 1 up to n. So that's exactly I have written. So therefore what I am having, so if I take k greater or equal to that capital N star, I know the definition of my distance, Euclidean distance in Rn, that means xk minus L square, which is nothing but component wise differential square, and each of the things I can make less than epsilon star square. So that means distance between xk1 minus L1 is less than epsilon star. So therefore square is greater or equal to epsilon star square. So I have n many terms, so I have n time epsilon star square, and as I told you, a given epsilon, this is nothing but the adjustment, so therefore you can make it epsilon square. So that means what I am getting, so that means I am saying that given epsilon, I can make the distance between xk minus L which is less than epsilon for all k greater or equal to n naught, and that is nothing but the convergence of the sequence capital Xk to L. Okay. So that means what I proved is that start with a sequence capital Xk in n dimensional Euclidean space, then we have the corresponding n component sequence in R, real line. Then I said that capital Xk converges to capital L in Rn if and only if all the component sequence converges, and where it converges, if capital L is equal to L1, L2, Ln, small l1, small l2 up to small ln, then the corresponding component sequence converges to small l1, small l2, small ln. Let's see some examples. Okay, in R2 I have, so this is a sequence in R2, so these are the component sequence we know, and I am saying that this is converges to L, and this is very kind of straightforward. Why? Because the first component sequence I know it converges to 0, second component sequence this one converges to 0, so therefore it converges to 1, so therefore it converges to 0, 1. So this is the kind of, just by using the earlier theorem I can say that, because I know the convergence of the component sequence, so therefore I know the convergence of the full sequence xk in R2. Similarly, so take a sequence in Rn whose each component sequence is a constant sequence CCC, so therefore the each of the component sequence converges to C up to n time, so therefore the full convergence sequence converges to this point. Now let's see some example of a divergent sequence. So consider this sequence xk in R2. So look, what are the component sequence? One of the component sequence is -1 to the power k, and another one is the constant sequence. Constant sequence I know it converges, but what about the first component sequence? It is first term is -1, then +1, -1, +1, and I already discussed that it is an oscillating sequence, it is not a convergent sequence. So therefore by the earlier theorem, since one of the component sequence it diverges, so therefore the full sequence is divergent. Similarly in R3, so this is a sequence in R3. What are the component sequence? First one is k, second one is the constant sequence, third one is the 1 by k. Now second component sequence converges because it's a constant sequence, converges to 1. Third one is converges to 0, this is converges to 1. But what will happen in the first component sequence? It's a divergent sequence. So therefore, if I apply my earlier theorem, since one of the component sequence is a divergent sequence, so therefore the full sequence xk is divergent. Okay. So this is another results, like in R we know if a sequence converges to some point and that limit has to be unique. Similarly, the similar sort of fact is true in the context of Rn. So that means if I have a sequence xk in Rn, suppose sequence converges to L1, this is converges to L2, then I will have the L1 has to be equal to L2. That means limit of the convergent sequence is unique. Proof is also straightforward. What I will do, I will have the epsilon by 2 argument. So that means start and epsilon is positive. Again, this is just the adjustment. Suppose epsilon star is equal to epsilon by 2. Now what is given? Xk converges to L1. This is given. So therefore, given that epsilon star, I can have the existence of K1 such that norm of xk minus L1, which is less than epsilon star, for all k greater equal to K1. Similarly, since xk converges to L2, given that epsilon star, I can have the existence of one K2 such that norm of xk minus L2, which is less than epsilon star, for all k greater equal to K2. Now what I will do, take the maximum of K1, K2. Now if I take small k is greater equal to K star, you just have the estimate capital L1 minus capital L2. So this is norm of capital L1 minus capital L2, which is this just add and subtraction of xk minus xk plus xk. So this is the equality. Then what I will do, I will use the triangle inequality. So that means this norm is dominated by norm of xk minus L1 plus norm of xk minus L2, and since small k is greater equal to K star, so this is less than epsilon by star, this is less than epsilon by star, so this is 2 epsilon star, and because of the adjustment I have this epsilon. So what I proved? I proved that because of the convergence of the sequences capital Xk to L1 and L2, given any epsilon, I can have, I am saying that distance between L1 L2 which is less than epsilon. So now whatever epsilon I can take small, the distance between L1 and L2 is less than epsilon. So that will implies that we have only one choices, which is nothing but norm of L1 L2 is exactly equal to 0, and which will implies that L1 is equal to L2. Okay. So therefore, if I have a sequence xk in the n-dimensional Euclidean space, if it converges to some point, that point has to be unique. So there are some more results on convergence of sequences. That means if I have two sequences xk and yk in Rn, if xk converges to L, yk converges to M, then the sum converges to corresponding sum of the limits in Rn. If I take a scalar and if I consider the product, that means if I hit it by lambda with xk, if I consider the new sequence lambda xk, it converges to the lambda times the limit of the sequence xk, that means lambda times L. This is another nice properties, that if xk converges to L, then norm of xk, this is a real sequence which converges to norm of L in R. Okay. So let's think. So which result that we proved in R but is not appearing in my last slides? What is that? So I have a two sequences, sum is convergent, scalar multiple is convergent. What is remaining is the quotient. So in a real sequence, I can have the notion of, suppose An converges to L, Bn converges to some M, then I have the notion of An by Bn, because the division makes sense in R. Whereas if I in n-dimensional Euclidean space, then the quotient, that means division, is not available for vectors. So therefore, I cannot have the kind of questions like when the division will converge to some R. So that kind of notion is missing in the context of Rn, because I do not have the notions of divisions of two vectors. So now I want to introduce the notion of bounded sequences in Rn. Let me just see what is the definition of bounded sequence in R. So it is the definition that is you people are might familiar with in the real analysis. A sequence xk in R is bounded if there exists a natural number m such that modulus of xk which is less than m, and that is true for all k greater equal to n. That means if I have the modulus of the elements of the sequence, it is bounded by some fixed number for all k, then I will say that that sequence is bounded sequence. So this is called bounded sequence, and if a sequence xk is not bounded, then I will say that it is an unbounded sequence. Some examples, for example, xk is equal to 1 by k, it is a bounded sequence, because 1 by k, so I can bound the sequence by 1. So that means 1 by k which is less or equal to 1 for all k. This is also a bounded sequence. Why? Because modulus of minus 1 to the power k which is less or equal to 1 for all k. But this is not a bounded sequence, because what are the elements? Element is 1, 2, 3. So it is an increasing sequence. So you cannot have a fixed number such that all the terms of the sequence bounded by that number, because it is increasing 1, 2, 3, 4. So it is an unbounded sequence. What is the notion of bounded sequence in Rn? Okay, same. If I have a sequence xk in Rn, I will say that it is bounded if there exists a positive number such that norm of xk is less than m for all k. So that means earlier I have the modulus in real line. Now I am just replacing modulus by norm in the context of Rn. Things will be same. So therefore, I will say that a sequence xk is bounded if norm of xk which is less than m for some fixed number m for all k. If this is true, then I will say that capital Xk is a bounded sequence, and if a sequence xk is not bounded, then it is an unbounded sequence. Definition or some examples. So for example, this sequence, it is a bounded sequence. Why? Because, okay, one more fact, later slides I will discuss. As I told you that given a sequence capital Xk in Rn, I will have the corresponding component sequence, and then I can make some conclusion on the full sequence xk in terms of the component sequence. Here also, if the full sequence capital Xk is bounded, then the corresponding component sequence is bounded. If the component sequence is bounded, then my full sequence is bounded. So that's kind of theorem I will prove in my next slides. So therefore, now look, so this is xk. Of course, you can just prove it directly, it is a bounded sequence. That means what? You have to define what is norm of xk, which is nothing but 1 by k square plus 1, and which is always bounded by square root of 2, and this is true for all k. So that's fine. That one of the just using the definition you can prove it. Later also I can give the argument that this is a component sequence bounded, this is a component sequence bounded, and therefore it is a bounded sequence. Similarly here, it is also not a bounded sequence. Why? Of course, one of the argument is that its component sequence, it is unbounded. Another is that if I take the norm of xk, what is this? This is square root of 1 plus k square. Now this k is an increasing sequence. We cannot have a fixed number such that this is less than m for all k, and therefore it is unbounded. It's not a bounded sequence. What is the moral? So that means concept of bounded sequence in Rn is essentially same as that of concept of bounded sequence in R. So I am just replacing mod by corresponding norm. Okay. So now, as I told you that there is a relations between the bounded sequence in Rn and the corresponding bounded sequence in R. So this is the one. So if I have a sequence capital Xk, these are the corresponding component sequence in R. So then capital Xk is bounded if and only if all the component sequence in R, these are also bounded. It is straightforward to prove. You just use the definition of norm of Xk and the definitions of corresponding bounded sequence in R or Rn, then you will be able to prove it. Okay. So there is one observation I should say, that convergent sequence implies bounded sequence, but the converse is not true. So what is the theorem? If I have a sequence xk in Rn, then if xk converges, then xk is bounded, but the converse is not true. Now, how do I prove it? So if a sequence xk, it converges. Suppose this sequence xk converges to capital L in Rn. Then if you remember in my last slides, I show that if capital Xk converges to L, then norm of Xk which is converges to modulus or norm of L. So that kind of things I have already discussed. So Xk converges to L implies norm of Xk, this sequence converges to norm of L. Now using that fact, it will be proved that Xk is bounded. Why? This is okay, because since norm of Xk is converges to L, so therefore I can say that given epsilon is equal to 1, I can make the distance between norm of Xk minus norm of L, which is less than epsilon for all k greater equal to some natural number n naught, that I can do because of the convergence of the sequence norm of Xk converges to norm L. Okay. So therefore what I will have? So I will have norm of Xk which is less than, so this is my 1, right. So norm of L plus 1 for all k greater equal to n naught, that is there. So next what I will do? I will do take m be the max of norm of x1 comma norm of x k minus 1 comma norm of L plus 1. If I take m is the maximum, because you see norm of xk which is less than norm of L plus 1 for all k greater equal to n naught. So what is remaining? I think this should not be k, this should be I think n naught minus 1. So therefore, what is remaining is that norm of x1, norm of x2 up to norm of x suffix n naught minus 1. So that I do not know what is going on there, but rest, that means k greater equal to n naught, x n naught, norm of x n naught, norm of x n naught plus 1, norm of x n naught plus 2, all are bounded by norm L plus 1. So if I take the a maximum of this norm of x1 up to norm of x n naught minus 1, comma norm of L plus 1, and this is a finite number, so I will have the existence of number m. So therefore, with that m, I can easily say that norm of xk, which is lesser or equal to that m, and now this is true for all k in n. So therefore, if my sequence xk converges to L, and this is nothing but the definition of bounded sequence, so therefore your sequence xa is bounded. So if my sequence xk converges in Rn, that means in dimensional equivalent space, it implies that my sequence xk is bounded, but the converse is not true. That means I have the existence of bounded sequence which need not be convergent. For example, this is one. So this is a bounded sequence. What is the norm? Again, as I told you, component sequence convergent. This is 1 by k, it is bounded. Component sequence, this is bounded by 1. This is also bounded by 1. So therefore, the sequence capital Xk, it's bounded because all the component sequences are bounded. But this is not convergent. Why? Because first component sequence convergent, but what about the second one? Second one actually oscillating. But I know that a sequence xk in Rn which is convergent means all the component sequence should converge. This is not going on here, so this is not a convergent sequence. So therefore, I have the existence of bounded sequence which is not convergent. Okay, so now again to think what is the missing for this sequence in Rn. Why the concept of, so now in R or real line, I know the concept of monotonically increasing sequence, monotonically decreasing sequence, but that is not possible in Rn. Why? Because now you can easily guess that no order relation like less than or greater than, that is not possible in Rn. In R, I can compare two elements. If I take two elements or 2 points in R, I can compare. That means which one is greater than, which one is smaller than. But in Rn, there is no such kind of order relation. So therefore, the concept of monotonically increasing sequence, monotonically decreasing sequence is not possible. And similarly, we do not have the concept of limit superior or limit inferior in the context of Rn. In R, we will have because we have order relations, but in Rn, we do not have. Okay, so yeah, so this is the answer. There is no order relation, and hence no concept of supremum and infimum in Rn. Now there is another notion of Cauchy sequence that you know in R. In R, what is the notion of Cauchy sequence? A sequence xk in R is Cauchy if for any epsilon such number n naught such that I can two elements, that means xk minus xl, which is less than epsilon for all k greater equal to n naught, for all l greater equal to n naught. So that means, so a sequence xk in R is a Cauchy sequence if given epsilon I can find the existence of natural number such that the distance between any two elements of this sequence which is less than epsilon for all k l greater equal to that n naught. So what is the example? So this is first sequence x 1 by k. So this is a Cauchy sequence. In fact, later on I will prove that if a sequence is a real sequence, you know that if a real sequence is convergent, then it is a Cauchy sequence. Now this sequence is a convergent sequence converging to 0, and therefore is a Cauchy sequence. And of course, by definition also you will have this kind of given epsilon, you can make the points like 1 by k1 and 1 by k2 difference between, you can make this is less than epsilon for all k1 k2 greater equal to some number. This is not a Cauchy sequence because it is not convergent, because in real line we know that Cauchy sequence and convergent sequence, these two are equivalent since it is not convergent and it is not Cauchy. This is also not Cauchy sequence, which is what kind of sequence? It is 1, 2, 3, 4. So what is the difference between any two consecutive term? It is 1. So I cannot make this is arbitrarily less than epsilon for all k. So all k greater equal to some n naught. This is not possible because you have the fixed distance between any two consecutive terms. So therefore it is not a Cauchy sequence. Or also you can talk about that it is not convergent and hence it is not Cauchy. What is the notion of Cauchy sequence in Rn? Okay, similar sort of notions I can give. Instead of modulus, I am just replacing by norm. Again, a sequence xk in Rn is Cauchy if for each epsilon there exists a natural number n naught such that norm of xk minus xl, which is less than epsilon for all k greater than n naught and l greater than n naught. Same thing, just I am replacing modulus by norm. So if this thing is true, I will say that my sequence is a Cauchy sequence. Some examples, again take this sequence xk in the 3-dimensional Euclidean space, it is a Cauchy sequence. You can directly use the definitions norm of xk minus, so you can have the existence of 1 n naught given epsilon, so that this is true, or in terms of the component sequence you will prove. In my later slide I have the, or one can prove that Cauchy existence or kind of Cauchy sequence of capital xk in Rn implies the Cauchy sequence of the component. So, Cauchy sequence of xk in Rn implied the Cauchy sequence of the component sequence in R. So, now look, so this is my xk in R3. So, what are the component sequence? 1 by k 1 and 1 by 3 to the power k. So, all are convergent sequence. That means all are Cauchy sequence in R, and therefore, the full sequence capital Xk in R3 is a Cauchy sequence. What about this one? So, again, what are the component sequence? This is one component sequence minus 1 to the power k. This is 1 by k. This is k. So, this is not a convergent sequence. So, therefore, it is not a Cauchy sequence. It is also not convergent. It is not Cauchy. So, therefore, the full sequence capital Xk is not a Cauchy sequence in R3. So, there is a relation between Cauchy sequence of xk in Rn and the Cauchy sequence of the component sequence in R. What is the moral? So, as I said, so concept of Cauchy sequence in Rn is essentially same as that of the concept of Cauchy sequence in R. In other words, whatever the definition is available in R, I am just doing the similar kind of things, except the modulus is replaced by the corresponding norm. That means the distance in R, whatever I have the usual distance, now I am replacing the same definition by the notion of distance in Rn. Okay, so this is the one. So, as I said, that means that if I have the Cauchy sequence of the sequence capital Xk in the n dimensional Euclidean space, then I will have corresponding n component sequence in R. What can I say about the Cauchiness of those sequences? So, this is a theorem. So, let Xk be a sequence in Rn, then the sequence xk which is Cauchy if and only if all the component sequence, these are Cauchy sequence. Again, this is proof is very straightforward. What we have to do, you just use the definition of Euclidean norm. So, that means suppose this is Cauchy, that means given epsilon I can make this is less than epsilon for all k l greater equal to n naught, then you just use the definition of norm of xk minus l. So, that means square root of what is called xk1 minus xl1, this is square up to xkn minus xln square, which is less than epsilon for this n naught, and then use that one of the, this is sum of positive numbers, as I already discussed that one of the term is lesser equal to the sum of positive n square, and which is dominated by epsilon. So, using that kind of argument, you can prove that if my full sequence xk which is Cauchy in Rn, then the component sequence is Cauchy. If the component sequence is Cauchy sequence, then the full sequence is Cauchy, because component sequence, how many component sequence we have? Only finitely many, and that is important, finitely many, to conclude that the full sequence xk is Cauchy. Okay. So, this is another result, I just say that. So, this is the what is the relation between Cauchy sequence and convergent sequence. So, we have observed that the equivalence between Cauchy sequence and convergent sequence. That means, if I have a sequence xk in n dimensional Euclidean space, then xk is Cauchy if and only if xk is convergent. So, now let us come back to the definition of subsequences. So, what is subsequences? I think you people are familiar with the definition of subsequences in real line. Now, similar sort of definitions will be there in the context of n dimensional Euclidean space. What is that? So, start with a sequence capital xk in n dimensional Euclidean space, then what you do, you start with a km. It is a strictly increasing sequence of natural numbers. So, that means you have a sequence of natural numbers like k. What you do, you take a strictly increasing sequence km subset of k. Okay. Once I have this strictly increasing sequence of natural numbers, now I want to form a sequence x suffix km. So, instead of k, I am having km. So, this is a subsequence of the sequence xk. For example, so take this sequence xk. So, these are the component sequences sin k by k, 1 1 by 2 to the power k. Now, if I take a strictly increasing sequence subsequence of natural numbers, so let it be km is equal to 3m. So, therefore, certainly 3m is contained in the natural number sequence m. Now, if I take the corresponding x suffix km, which is nothing but sin 3m divided by 3m, comma 1, and third one is the 1 by 2 to the power 3m. So, therefore, this is certainly a subsequence of the given sequence xk. The definition of subsequence you are familiar with in real line. The similar sort of definitions is available in the context of n dimensional Euclidean space. So, this is our result concerning subsequence and given sequence. So, what is the result? It says that if I have a sequence xk in Rn, then and suppose let L is an element in Rn, then the sequence xk which is converges to L if and only if each of the subsequence xk of capital Xk converges to L. Similar sort of theorem is also true in the context of real numbers. That means, if I have a sequence x, suppose if I have a sequence small xk in real numbers, if and only if all subsequence of that sequence converges, that you are familiar with that. Similar sort of results it's true in the context of n-dimensional Euclidean space. That is, if I have a sequence capital Xk in n-dimensional Euclidean space which converges to capital L, if and only if each subsequence xkm which is also converges to L, and vice versa. That means, if I have all the subsequence of xk converges to the same point, then the given sequence also converges to L. Okay, I think I should stop here. This is concerning sequences, subsequences, Cauchy sequences convergence. In my next lecture, I will talk about functions from m-dimensional Euclidean space to n-dimensional Euclidean space, and the concept of limit and continuity, what sort of definitions will be true in the context of several variable functions. I think for the timing I should stop here. Thank you. We will see you in the next lecture.